Hi, welcome to video 3. We're going to look at some ways to find limits and some properties of limits that we can use to help us. Again, we're going to do some simplification. We're going to be using graphs, and then this new idea of something called the sandwich theorem is going to show up. Okay, so these are just some basic properties of limits. This one says the limit as x approaches a of c equals c. Okay, so what the heck does that mean? Well, if c is a constant, not a variable. So imagine you had an equation like y equals 3 or y equals 7. If you're talking about a graph that looks like that, you're talking about a graph that just has a horizontal line at that value. So no matter what you approach, your y value is going to be that c value. So if it's just like the limit as x approaches whatever of 5, you're always going to get out of 5. Okay, for the second one, we've got the limit as x approaches a of x. Well, literally, you guys could just see that you could plug in a and you're going to get out a. So it's just a straight up plug-in relationship. Now we get a little more complicated. This one says if you're adding two different functions together or subtracting, you can do the limit of them separately and then add them or subtract them. Same thing in number 4. If you have the limit of a product, you can do the limit separately and then take their product. There is one little interesting piece to this. I'm going to show you an example at the end. Same thing with division. Obviously here, if the bottom ends up giving you a 0, you're going to have some issues, but in general, that's fine. Some more properties that you can look at. If you've got a constant, you basically could bring it out to begin with and then do the function first. This is kind of a simplifying technique. The power property, which says that you would just end up with a to the end. A lot of these are just very intuitive. And then this one, if you have a power of a function, you can find the limit first and then raise it to the power. These are just ways to make finding the limit a little easier. Here, I think this makes sense. You're plugging a into the function, so you get whatever you get when you plug in a. Here, you're getting whatever you plug in a to q. These are basically the same type of idea, just showing you two different functions. This one is dealing with roots. So again, if you plug in a root, you get the root. And again, if you have a root of a function, you can plug it in and find the limit of the function first and then take the root. So things to look at. We also have something here called the sandwich theorem. And now this part we will talk about later. In the sandwich theorem, uh, I'll explain it more. Basically, you're saying if you have a function that is always in between the values of f and g. So what I mean, remember, these are talking about y values. So basically, if the y value of the f function is always smaller than the h, and that's always smaller than the g, so graphically, you could have something that kind of looks like this. Like, let's say that this is the f of x function, which is the one that's always below. Perhaps this is my g function, and perhaps this guy in the middle is my h of x function. So what they're saying again is that if the f of x is always smaller than the g of x and the h of x always fits in between those two. Now notice the or equal to's, that's important. Then if as you get closer to a, which I'm going to mark right here, if this red graph f approaches this L value for A and G, the higher one, also approaches A, then that means that the one that's squeezed in the middle, H, has to also approach this L. You're basically forcing that middle black function, which again does not have to be a horizontal line, to also approach that same L value. So we'll look at that later. Okay, so only a few examples to look at today. And this first one is that squeeze theorem example. So we want to find the limit as x approaches 0 of this. Now, if I plug this in, I get a 1 over 0, which is an undefined situation. And I have no way of factoring that apart, and so I can't use techniques that I've used in the past. So what I'm going to do is attack this by using the squeeze theorem. So I'll write that at the top just so you know what I'm doing. Okay. So first I have to start with a function that I know is between two other values or two other functions. So I'm going to just use this part and go from there. Okay, so what do I know about sine of a function? Well, I know, and you should know this from what the graph of sine looks like. Remember, sine looks like this. And when you have the sine of a function, notice there's nothing on the outside. I'm not adding anything. When I have a sine graph, I know that that sine graph has to fluctuate between being -1 and 1 for its y values. So I can literally say, I know this has to be between -1 and 1. This is true. I know it's true because of the graph of sine. Okay. So then what I really want though is all of that. And so to create all of that, I would have to multiply this middle part by an x squared. Okay, done. Now, if I multiply this by an x squared, and this is the kind of nice part, because it's x squared is always going to be a positive number, which means that when I multiply this part by x squared and this part by x squared, it's not going to affect my inequality. So I basically end up with a negative x squared has to be less than or equal to x squared sine x of 1, or excuse me, sine of 1 over x, which has to be smaller than x squared. Okay. So remember, the whole point is we want to look at as it approaches 0. So our squeeze theorem says this. If I look at the limit as x approaches 0 for the lower one of negative x squared, and then I look as x approaches 0 for my larger one, positive x squared, if those two things end up being the same value, then the one in the middle has to be that same value. So let's see. Well, I can plug in 0. Remember, we always plug it in to begin with. So 0 squared times a negative is 0. If I plug in 0 here, 0 squared is 0. Because these two approach 0 on either end as you look at 0, that means the middle is forced to approach 0 as well. That's the squeeze theorem. So the limit as x approaches 0 for the middle has to be 0. That's how the squeeze theorem works. We're going to use this a lot with trig functions, and finding derivatives of trig functions in the future. So we will see that, but this is just one example. Okay, so let's look at a couple of tricky examples because honestly, you guys will be probably fine with most of the problem set, but there are a couple of interesting pieces. So I'm going to start with actually this guy up here in the corner. He's the easiest of the three, and then I'll move on to some of the trickier things. Okay, so this one asked me to find the limit as x approaches 3 of f of x times g of x. Technically, those are together, so I'll do that. Now, my property states that I can find the limit as x approaches 3 of f of x and then multiply that by what I get when I do it for g of x. So let's take a look. Is there a limit as I approach 3 for f of x? Now, I'm going to take some liberty here and continue this graph, and I'm going to take some liberty here and continue this graph. You would need it to continue, so I'm going to go ahead and do that just so we can do this question. So as I approach 3 for f of x, yep, it looks like I'm at -1 on either side. And for g of x, as I approach 3, it looks like I'm at +1. So this value would have a limit of -1. Pretty easy. Now let's go down and look at this guy. This one has something very interesting happen, and I'm going to take my time explaining this. So if I split these up, I get the limit as x approaches 2 for f of x. Well, let's go over here. As I approach 2 for f of x, whoa. Do you guys see as I approach 2, this side's going to 1, this side's going to -1. So technically that side doesn't exist, right? Okay. That's obviously a problem. Let's just go over to g of x for the fun of it. If I go to g of x and I look at as it approaches 2, clearly that one does exist and it's approaching 0. The problem is I basically have does not exist times 0, right? Which if we had does not exist times anything else, we would say that it doesn't exist because you can't figure this out. But 0 actually has a very special property here because of what happens when you multiply by 0. So think about this. Let's just do one side at a time, okay? If I look from the left, let's just see what happens if I multiply them. So f of x, as it approaches 2 from the left, so here we go, is going towards 1. Now, let's see what g of x is from the left. g of x from the left as we approach 2 is 0. So if I multiply these two things together, so that kind of looks like this. If I multiplied the limit as x approaches 2 from the left of f of x times g of x, so that would be, we said we got a 1 for the f of x times 0. So on the left, it approaches 0 because, again, this one was 0, this one was 1, so we get 0. If we look at the limit as x approaches 2 from the right, I get, let's see, on this side, I'm approaching -1 for 2. And on the right for g, I'm approaching 0, which we already knew. Now, look at what's interesting about this. Because this was a 0, it made this a 0 in general. Like, it didn't really matter what it approached on that side or that side, because when you multiply by a 0, you get a 0. This is a very special case. So what I'm telling you is, normally if one of them does not exist, you can't do it. But if one of them does not exist and the other is 0, it's always going to make it 0 on either side, so you actually can do it. So the answer to this one actually does end up being 0, believe it or not. Okay? If you need to go through that, stop the video, rewind, and watch that a couple more times until it makes sense, go for it. Okay, to something I think is a little bit easier. Let's look at the limit as x approaches 0 of g of f of x. This is composition. This is when you have one function inside of the other. And the way that we do this is we actually do the limit as x approaches 0 of f of x. We get that value, and then we plug it in for g. So it's kind of like you're doing this. Okay, so we're going to do the inside first, and then we're going to see what g is at that value. So let's hope that there's a value at 0 for f of x. Here we go. Up here to 0, as we approach 0 on both sides, yep, we're at 2. So this is the same thing as saying g of 2, because the limit here was 2. Now, do we have a value for g of 2? Let's go over to 2. Yep, my value at g of 2 is 0. So I do have a value there. Okay? Okay, so you're going to get a chance to practice these as you go through your problem set. Good luck. We will definitely go over some questions on these in class because they do get a little tricky. But if you need to go back and look at some of these examples I've went through, listen to them again, that could be helpful.